Hi, I am Jinhyeok Choi, an MS student in the School of Computing at KAIST. I'm a member of the Big Data Intelligence Lab led by Professor Joyce Jiyoung Whang. I'll present our paper, SpoT-Mamba, Learning Long-Range Dependency on Spatial-Temporal Graphs with Selective State Spaces. A spatial-temporal graph, or STG in short, is a type of data structure used to represent data that changes across both space and time. STGs are widely used in various fields, such as urban traffic networks, weather data, and skeleton-based human actions. This picture shows the traffic flow of New York City's road network from 6 a.m. to 8 p.m. The colors indicate the traffic speed, green for fast-moving traffic, and red for slow-moving traffic. This example provides insight into how STGs can effectively model spatial-temporal information. In STGs, nodes are entities with spatial properties, and node features evolve over time. Edges represent relationships or connections between entities. For example, as shown in this figure, the road network can be represented as a graph for each time step, where the node features indicate the traffic flow on each road. Formally, an STG, denoted as script G, is defined by a set of script V, E, and X. Script V is a set of n nodes, and script E is a set of edges. Script X is a sequence of node features at each time step, which consists of n times the n-dimensional matrices. Given the historical observations for the previous t time steps, the goal of STG forecasting is to accurately predict the observations of the future t prime time steps. This can be considered as a sequence-to-sequence task with the STG forecasting model F. In STGs, the node features evolve over time, and these changes propagate throughout the entire graph. Spatial-temporal graph neural networks, or STGNNs in short, have emerged as a powerful tool for capturing both spatial and temporal dependencies in STGs. Many of those methods employ graph neural networks, or GNNs in short, to exploit spatial dependencies inherent in the graph structures and integrate them with transformers to capture temporal dependencies. However, they often face challenges in handling long-range spatial dependencies, as they simply stack GNN layers. In addition, the significant computational overhead and complexity of self-attention mechanism are being highlighted as major concerns. To address these issues, we introduced SpoT-Mamba, a new spatial temporal graph forecasting framework based on the recently proposed state space model called Mamba. SpoT-Mamba uses a Mamba-based sequence modeling architecture to better capture long-range dependencies. First, let me explain the preliminaries for SpoT-Mamba. A state space model, or SSM, is a mathematical framework used to represent dynamic continuous systems by their states at a given time t. The SSM learns how to transform the input signal xt into the latent state ht, which is used to model the system dynamics. Then, it predicts output yt using these two key equations. To adapt the SSM for discrete input sequences instead of continuous signals, parameters a and b are discretized with a step size delta. Then, we can formulate the discretized SSM in two ways, a recurrent form and a convolutional form. The recurrent form allows for efficient inference in SSMs, while the convolutional form enables parallelizable training. However, SSMs struggle with handling discrete and information-dense data such as text. This limitation arises from the linear time invariant constraint, which requires that the parameters of SSM remain fixed across all time steps. A recently proposed structured state space sequence model, Mamba, removes this constraint by modifying b, c, and the step size delta to functions of the input sequence. In this way, Mamba can selectively recur or ignore information in an input-dependent manner, while maintaining linear complexity in sequence length. In this work, we introduced a new framework that integrates Mamba's sequence scanning capabilities to STG forecasting. SpoT-Mamba is mainly composed of three components. First, it generates sequences for each node using three work algorithms to extract diverse local and global structural information. Second, SpoT-Mamba scans these work sequences for each node to generate node embeddings using bidirectional Mamba blocks. Third, by scanning along the temporal axis with Mamba blocks, SpoT-Mamba forecasts the node features for future time steps. I will explain each of these components in more detail in the following slides. To generate node sequences with diverse structural information, we adopt three well-known work algorithms: breadth-first search, depth-first search, and random works. Each work algorithm captures different aspects of the neighborhood structure of the target node. Next, SpoT-Mamba performs bidirectional scans on the different types of work sequences of length k for each node. This process creates representations for each work sequence, capturing both short and long-range structural information for each node's neighborhood. The representations of work sequences are transformed into that of the target node via pointwise convolution. After that, using MLP, SpoT-Mamba integrates three different types of representations into node embeddings. Instead of simply stacking GNN layers, we employ Mamba-based sequence modeling to generate node embeddings from various work sequences. This method effectively captures long-range spatial dependencies by scanning and aggregating the multi-way work sequences. This picture shows the overall STG forecasting flow of SpoT-Mamba. SpoT-Mamba adopts learnable day of week and time step of day embeddings to capture repetitive patterns over both short and long periods in STGs. These embeddings are concatenated with the node embedding for each time step. Then, SpoT-Mamba scans these sequences along the time axis with Mamba blocks. Finally, SpoT-Mamba integrates global information from all nodes at each time step using transformer. We also use a regression layer to forecast the attributes of each node for future time steps. To accurately predict the temporal trajectory and ensure robustness to outliers, SpoT-Mamba is trained with the Hoover loss, which combines the L1 and L2 norms. We evaluated SpoT-Mamba on the PAMS-04 dataset, a real-world traffic flow forecasting benchmark. PAMS-04 contains highway traffic flow data collected from the California Department of Transportation's Performance Measurement System. In this dataset, nodes represent sensors, and edges are created when two sensors are on the same node. Traffic data in PAMS-04 is collected every 5 minutes. We set the input and prediction intervals to 1 hour. The statistics of PAMS-04 are shown in the table. We compared SpoT-Mamba with several baselines using various methods, including STGNS and transformers. We considered 5 methods for STGNS and 3 methods for attention-based methods. Additionally, other types of methods such as ST-norm, HI, and STID are also considered. The left table shows the traffic forecasting performance of the baselines and SpoT-Mamba in terms of mean absolute error, root mean square error, and mean absolute percentage error. For all 3 metrics, lower values indicate better performance. For each evaluation metric, the best result is highlighted in blue, and the second best result is highlighted in yellow. Additionally, we'll rank all the methods across the evaluation metrics and compute their average ranks. We can see that SpoT-Mamba consistently show promising results across all metrics, recording the best overall average rank among all methods. This suggests that Mamba's selective recurrent scan effectively models spatio-temporal dependencies in STGs. We visualized SpoT-Mamba's predictions and the ground truth time series. We randomly selected 4 nodes and visualized their predictions starting from an arbitrary time step within a test split. And each case covers 2 days. The blue line represents the ground truth, and the orange line denotes the predicted traffic data. We can see that the predicted time series closely aligns with the ground truth data. SpoT-Mamba's predictions tend to follow the overall trends accurately and are less prone to noise. Additionally, we conducted ablation studies of SpoT-Mamba. In these studies, we replaced the Mamba blocks used in the walk sequence embedding and the temporal scan with transformer encoders. The walk sequence embedding is denoted as walk scan, and the temporal scan is denoted as temporal scan. We observed differences in performance depending on which type of scan module was replaced. Specifically, when transformer encoders replaced the walk scan, the overall performance decreased. In contrast, replacing only the Mamba blocks for the temporal scan with transformer encoders had minimal impact on performance. This disparity can be attributed to the inherent differences between Mamba and transformer, along with the application of learnable embeddings. Mamba blocks accurately scan inputs, inherently considering the sequence order. In contrast, transformer encoders do not recognize input sequence order by themselves. Furthermore, while SpoT-Mamba utilizes learnable embeddings for temporal sequence, it does not apply such embeddings for walk sequences. As a result, transformer encoders struggle to perceive the order in walk sequences, even though they perform well with temporal sequences. Notably, the maximum GPU memory usage increases by about 4 times when we use transformer for temporal scan. In this paper, we explore STG forecasting and introduce a new Mamba-based STG forecasting framework, SpoT-Mamba. SpoT-Mamba extracts diverse local and global structural information by utilizing BFS, DFS, and landmarks. Then, it utilizes Mamba blocks to scan multi-way walk sequences and temporal sequences. This approach effectively captures the long-range spatio-temporal dependencies in STGs, enhancing forecasting accuracy on complex graph structures. SpoT-Mamba shows promising results on the real-world traffic forecasting benchmark PAMS-04. Our codes are available at this link, and you can find more materials on our homepage. If you have any questions, feel free to reach out to us via email. Thank you.